So welcome everyone. So today's discussion will be about representation of, so to say, 1D as members or stiffeners across different industries. And basically, I try to depict some of the tools and latest update over the tools that we've been releasing over years across different applications that can span from automotive, from concept modeling to shipbuilding, aircraft modeling or civil engineering. And just in short, I mentioned about members or stiffeners and being everywhere, just that the name changed. So we might call them members or pillars or columns, stiffeners, scantling, and so on. But I try to illustrate what basically are stiffened structure and what is new. So as an high-level summary and from the update standpoint, because everything I will show today, not everything is new, but we keep on adding functionality and enhancing the performance. So for this coming release, main point will be on the usability. I've been refactor all of the context dealing with 1D meshing and editing. While it's minor, was to say that we know, at least for OptiStruct now, supports the taper beam 3D visualization. The main development is about the ongoing integration of section property calculation with a sketcher. So we are adding a new configuration for beam section called elastic section that can interact with the sketcher and support multi-material, so that's a brand new engine. We'll see some, the main journeys that we will try to depict today will be model reduction, optimization, and let's say model inflate. So as such, we'll go through the latest update on a beam to surface as well as beam to solid. And was to mention the last context that we have been releasing to support VAPS, which is a partner program tool, but coupled with OptiStruct. And again, from a performance standpoint, so we made some huge improvement in our section property tools and consolidation. So where did we start from? So regarding the 1D meshing, till 2022, we used to have several tools spread in multiple locations. So that was in a, let's say, mesh page. And we used to have a page, I say used because it's now phased out, called Marine. In a 1D, we had lots of tools to generate 1D or update 1D property and review an existing mesh. And in Marine, we had a special flavor which would take advantage of the instrumentations that our CAD.io readers are doing from a format like Viva Marine, OCX, or Ferran, for which this tool was able to auto-generate all of the scantling for such a CAD from just orphan lines. And we had some tools for section property, but used to generate some generic section per se. And mesh inflate was well done in Marine, so it was already there as called a beam to shell, but very limited to standard section, and property was even lost after inflate. So first thing I want to mention that we have consolidated each and every tools, and we release two sets of tools, one called member and one called stiffener mesh. Then we separate the edit beam to a proper context, top level context. And then from a sectional property point of view, the engine, we have extended the engine to support elastic section and shell section, and also, as mentioned, the VAP section. We'll go through it. And now we have, instead of a beam to shell, we have two siblings, which are mesh inflate, which is a beam to shell from standard and shell beam section, and also beam to solid. And just was to mention that, as said, Marine page has been removed, but on the other hand, we are adding another page called concept, which is off by default, onto which we migrated some legacy tool like Stiffen Panel Mesher. and also some tools that was already there, well hidden behind the 2D mesh, which are doublers and bulkhead, because those one are basically creating some stiffener on a mini auto open section. Yeah. So let's see first the meshing tools. So what we have from a stiffener and member meshing. So I'd like to illustrate quickly, and I have demo models to do it, but I will go first with some few video just to see the different sets of tools. So what's the main difference in HyperWorks from a member and stiffener? That a member is nothing but a 1D meshing of lines being free or surface edges. And we have an engineering name called beams or rods and pipes, and we auto-generate a proper element type and property based on this. But on the other hand, we have a stiffener mesh, which this one requires to have some shell mesh. So we will stiffen a shell mesh by using any kind of source being nodes, surface edges, or free line. And in this case, we can mesh by proximity. The orientation can be driven by metadata if the CAD provides those one, or at worst case will be from the shell normal. And even property can come from metadata. So I try to illustrate with just two different examples what the member mesh is. So in the mesh page, member, we can select, let's say, free lines. And in this small building example, I will just select, let's select a tube and just generate a mesh as a column. So nothing rocket science here. Just since it's a column, a tube, I didn't even provide the direction, but we could have done. And now switching to the stiffener mesh, yeah, if we want to reinforce the floor, in this case, we can select which type of element to be generated, which section, which in this case will be a channel. And let's go with the floor edges. So by clicking on mesh, we will sample 1D element on each and every shell edges. And it will come with an auto orientation along the shell normal and offset on the normal. Just that here, by default, it goes on the shell top side. So if I want to have a stiffener below that plate, I can basically reorient it by 90 degrees. And we will re-offset along the shell positive normal in this case. So here we have several options to, let's say, reset to shear center, position at origin, or position on top or bottom of plates. And here we are done with this case. So let's go with a less trivial example, like that block ship block stiffeners. So in such a case, here we have a ship, yeah, and it has been read by from a Aveva Marine hull design, and we have a collection of parts being plane stiffeners or curved stiffeners, model as orphan lines. So they are not connected, no topology connection with the geometry itself, just some orphan line, but we have a collection of parts. Now, if we go to the stiffener mesh, we can simply select those orphan line and mesh them by proximity. So here again, we can select the type of property to generate. And let's see if we go with one particular stiffener group, which is an orphan line. So this one has a special metadata attached to it that come from the reader, which is directly the property. So we don't need to select property, and we can directly mesh and seed it. So as a matter of fact, we will have the 1D on top of each and every shell, properly oriented and offset. But in some cases, like in this whole example, Aveva reader had an issue, for instance, with the reflected part. So the reflection leads to a wrong orientation. We provide some sets of tools to change the orientation and change the x-axis. Just a quick view here, just to flip that x-axis. And even while here the offset is correct, just to show that how easy it is to change the side of the plate that we want to stiffen. Okay, so that was just a brief recap on tools that we do have. I won't spend much time on this one. I can do a live demo afterward, but just we used to have a tool called Stiffener panel in Aero, which was a legacy tool, where the main aim is to generate panels and stiffeners just from conceptual lines. So in this case, we do have a model with just a network. So it is tailored to a network of orthogonal lines. And in concept Stiffener panel, we can select those two sets, so the longitudinal lines, the lateral lines. And let's say we can refer to a reference property, being a composite or metallic. And we decide to create a bill of material from it. So here we see the reference panel, which has been identified from those lines, to which we can assign some beams along the longitudinal stiffeners and the lateral stiffeners. Let's say we create our frames here. And well, I'll fasten it a bit, but yeah. As a result, we have created a part assembly, which is made of a collection of stiffeners, panels, and even the stiffeners are decoupled in longitudinal stiffeners and lateral stiffeners, each of them being a single part. And panel will have a deep copy of the original properties that we have created. So this model is ready for optimization or design exploration later on. So it's more a concept design tools here. And we will extend this one with in a further release with parametric cutters. Okay. So once we review this meshing tool, I want to straighten the fact that we try to help a user to reduce a 3D model, generate mesh, well, let's say update it, optimize it, and then reinflate that model. So while that's not the main topic for today, well, I want to re-emphasize this nice workflow which has been released in 2022, which is skeleton modeling. So I won't go too much in detail for skeleton modeling because it has its own presentation, but worth to mention that we have introduced new concept in HyperMesh. So now we have a concept of a joint entity, where here we can create two joints defined by box on this auto. And once we get a member joint entity, we can generate members which goes from start join to end join. And this one can lively update and auto-create itself from the cross-section of elements here. And then generate a member entity, which is realized as a 1D element here. So just quickly, one of the goodies of this tool is to generate a symmetric member, so we can reflect the members. And main point of this demo is then to generate the perpendicular members from one to the other. And once we will get those a closed loop of members, generate a panel. By picking those four members, which are topological entity, we can generate 1D rep and a panel representation. So it was just a quick summary on skeleton modeling as a way to reduce the model. So now, let's say that you simply model with beams 1D and don't have that skeleton. As a recap to what already exists in 2022, we had one tool that was called section property, which aim was basically to update existing 1D, being able to create a cross-section of this 1D from surfaces, shell mesh, solids, considering the thickness, multi-materials, and some contact in parts. And we can even translate those 1D to reposition them at the proper location, being the section centroid or the shear center. But what's new? Now, we have been having a support for the shell beam section. Previously, it was only a generic section generated with auto weld. The main point I will describe now is this new elastic section configuration and its integration with a sketcher from Inspire Sketcher, which is integrated in HyperWorks now. and also the support of a composite section being compliant with VAPS. So as a first example of model reduction, while easy, I will go with a solid, let's say a solid frame, and I want to reduce that solid onto an equivalent 1D. So now, as such, I will simply sample some 1D element as a member element along the beam, let's say providing a size of 100. And my main interest is to go to that elastic section cutter. So selecting those target element, we'll select the solid as a source, and we can do 1 cut per element. So here we see a preview of each and every cut, and we can basically change a location of that cut along the parametric of each and every element. And once we, in this example, I ignore material, but we can have multiple solids or multiple sources with multi-material. Engine will take care of it, assuming that they are isotropic material. And now we can see the 3D visualization of the beam being generated. Here, I just adjust to not account for that hole. So as we can see, we have the overlaid solid and the resulting beam. Yeah? And if we switch off the solid, that's a 3D visualization of the beam being generated. And just it's a quick view of its neutral axis and a section property area, as well as the offset, which is applied to the element to match with its shear center location. Okay. One of the major announcements which has been done for this release is now the new elastic section, where you saw it in practice being generated from a donor solid. But on the other hand, we can support parametric section. So basically, here I have a model with a sketch. So if you are not familiar with sketch, that's the same module which is borrowed from Inspire sketch, and which is now available since 2022 in HyperMesh. And we can create a new configuration of beam section which refers to that sketch. And the moment we assign a sketch to a beam section, then the 3D visualization will come from that sketch directly. And whenever we update parameter, engine will update lively. So we will recalculate the section property from a sketch update, and a 3D visualization will be updated too. So an illustration of that one could be even to update the sketch, not only by parameter, but adding new member to new item to the sketch itself, like a plate. Can parameterize, and by switching off the sketcher mode, then engine should recalculate and 3D will come for free too. Just in this example, my beam is reverse compared to the sketch drawing, so plate will be on top. And just quickly changing the plate size. Okay, so a practical example. If we go back to my building before, I'd like to change the floor from a library of existing beam section. So now, on top of the 2 standard sections I had before, I will generate another beam section coming from a library, like the ESC library. If I go to my collection of sketches here, I will take the same sketch as before, so my eye section, and then again, just showing that it lively updates with the parameter. And now let's assign that sketch to the beam section. And what we will do then, we'll create a new property that refer to that beam section and reassign that property to those elements. By doing so, 3D view looks offsetted because the offset value came from the channel. So we can see the 3D visualization from the sketch and basically go to edit and re-offset to adjust element. Here we go. And again, just to show, if we change the flange width, we should see the 3D, while the offset will be off and need to be adjusted. Okay, so let me go faster. Now, considering the composite section, it's not exactly new in this release. It was there in the release before. We used to have a provision to support VAPs, but we made some improvement and create a new context for it. So for those not familiar with VAPs, it's really popular, and even outside of Aero now, for all of this new mobility, there is a huge trend to model such a blades or wing box by a 1D element with a section cut, because it will allow to have an accurate representation of the 1D slender structure dynamics, and coupled with aeroelasticity model, we can have a fast evaluation of structure stiffness and whether it flutter or not. So the main use case for such a structure is to do several slices and use VAPs, which is not neither Timonchenko nor Euler methodology, but use a variational analysis to accurately represent the stiffness matrix. And VAPs, which come from APA, is coupled with OptiStruct, and OptiStruct has a modified beam using VAPs. So now, let's say we use this model, which is made of laminate, PCOMG with several plies. And I just have, as an example here, one beam. So we have a new context called VAPs section. Out of a 1D element to be updated. We will update them from a cut on those source element. And generate a file at a given location. So let's say in temp here. So we literally inflate the mesh by considering each and every ply in the composite. And we see the matching between a 3D view and those ply. We have even provision to generate actual element, while here it's a purely graphical element, but we can generate some true element out of this mesh inflate. But that VAPs generated file now is used by a new property called PBML property, which is an OptiStruct property, referring to that VAPs file. And now we can run a simulation with OS coupled with VAPs. Okay, so I try to cover the cases where we come from the 3D world and try to generate 1D, either a members or stiffeners. But once we get those 1Ds, the main topic will be to do, let's say, some optimization, parameterization, and we might want to inflate the model back. So we used to have one functionality called beam to shell, which has been improved. And if I go back to my ship model here, starting from my bulb 1D, in inflate shell, I can generate some surfaces or shell mesh. And we do have multiple options to generate shells. So it can be fully decoupled with any size. Or if we use a beam node, we will make sure that we keep the connection with the original shell connected to that node. And not only we generate the surfaces plus shell mesh, but we assign a thickness to it. So we can do nodal thickness or property assignation. Yeah. And here it nicely represents the same shell mesh as the original bulb. So bulb is, so to say, one of the only beam section we have with this varying thickness, but we do support each and every standard section that way. The main new things, which I illustrate more with an auto model, is the support of a shell beam section. So let's say we do have such a model generated by skeleton, and we have 1D. And just here in this example, that 1D was not, it's a donor model which was not fine. So I just readjust the orientation of beams. To be more practical. And to avoid any mistake in offset, I will re-offset everything to match with the section centroid. So it allows not to have any issue with shear center or wrongly defined. But in the inflate, we have an option to say that the section match with its centroid. So surface will be defined correctly. And the point is that here we have several options for surface continuity. So by using really a small angle for vertex angle, just on this small part, we will generate, so to say, one surface per beam. So if we switch off the 3D visualization, it ends up to a surface per beam element. And from the original section, we keep straight segments, so that surface is really split in multiple surfaces. Here, by changing the vertex angle, we can generate some smooth surfaces. And now we can interpolate the shell part to be more smooth and result to a smooth interpolated surface. So in this pieces, we show that if we basically have multiple parts on a beam section and multiple beam sections refer to the same part, we make sure to create some lofted surfaces and mesh them and assign the proper thickness. So what we see here on screen is a shell mesh that results from this 1D inflate. And yeah, we don't see it here. I can do the demo afterward. We even create one part, one component per actual shell beam section part original. Okay. So generating surfaces and shell mesh was fine, but even although we do support the generate of solids, yet it's limited to standard section for now. Going back to this model where I'm using my standard section, so the tubes here and channels, we can directly convert them onto solids. And now end up to solid geometry being generated out of the beam. And worth to mention that we do support taper beam here. So even if you have a taper beam, that solid itself will render that taper beam. Okay. So I think I have some practical example. Whatever I shown before is really to be a demo here. I reload that model itself here to show whatever I was mentioning before, just for the 1D mesh. So in this example, while reading the file, we have a collection of parts and no 1D elements. So going to the Stiffener mesh, just doing Control A, selecting the type. So I didn't mention before, but we have engineering name here, beams and rod, and depending on it, we filter out the property that can be created. And based on that, you will filter out the properties that you can actually select. But if you don't go with a property approach, but select a beam section directly, here by selecting a property, it will result to create, in this case, C bar element and P bar. But if I go to P beam, then it will be C beam and P beam. And if I don't select anything but have a beam section assigned to part, it shall generate the 1D directly with the proper beam section assigned per part. So that's it finished. While it's not super large model, well, there is a bunch of 1D to be created and a bunch of parts to generate. It's done. Yeah. now it's done. So now if we basically switch it to 3D view, yeah, here we are, and offset, orientation, everything is correct. And as I was mentioning before, if we can, let's say we do change some of the beam section, like let's escape and go to that special beam section here. Select the beam section and let me change. Turn on 3D. As such, since I change the size, the offset is not correct anymore. So I can go to offset and reselect those components and let me replace it properly, accounting for the shell thickness. Yeah, switching shell thickness. And the main point is that now we can inflate it. Again, I can go with everything just to be faster. I go in this region, shell mesh. And if we use a size of 10, but in this case, use one of these two options, so section share center and create, we shall get a shell mesh which is disconnected because we don't forcefully extend those sections to the connected plate. What if we unzip and we want to honor the original topology, then by meshing it, now we have a connected mesh, and by switching on again 3D visualization, it should match. So more just said here, yes, this offset can't be honored anymore because we force a web to be connected to the shell in this case. So basically about that model. Let me switch something which works, I think, to this beam to shell. If I go again in this example, let me select this inflate, and let's select for now those curved region. Use this option, the vertex, small vertex angle, and create. We can see that we have exact same result as the beam section 3D view. But if we undo this operation, now we can even have something even worse, not smoothing each and any part, but do straight segment. If I do this, you can proceed. Proceed. Now we can see that it reflects each and every point that was in the original beam section itself. Control Z. And if we want to have something which is smoother, we can do a shell part, smooth part line, and proceed. And now we have something which is really smooth and interpolated. So I think as a better example, we can go with this one. And, in this example, we have a collection. That's the same model, but we do a scaling. So it was originally the same beam section, but this one has been scaled by 1.5%. And what the tool is doing, going to the mesh inflate. For shell section, we have several options to generate surfaces and mesh where we sort them. But the concept of part, so if you are not familiar with shell beam section, which is a legacy data in HyperMesh, if we edit in HyperBeam, you can see that first of all, the actual representation of those thin wall section is just point per point vertices. And each and every section has a concept of part, which are slightly different from the HyperMesh part. But here we have a collection of a part with attached thicknesses. And the moment we have multiple cross section, they can share the same part. So if it has been modeled in a way that multiple cross-section has the same part name, then by doing the conversion 1D to surfaces, we will make sure that we have a continuous transition. So to say, if we select those elements here and click on surface, D, and let's say we do Control A, let's see, color. Yeah. Now we have surfaces which has been interpolated and across various cross section. If we go with model, I built in this model the reference line that was to the beam section. Superimpose those one with a 3D visualization. It's not that easy to see with 3D visualization because taper beam here for shell is not well rendered. But if we superimpose the surfaces on top of those lines, switch off the 3D visualization, we can see, well, my bad. If I go back there and reselect those one, I should say that I will match here the centroid because those one has been moved to centroid. Good. Or perhaps, oh, sorry. Just before, I simply slightly morph this one compared to the line. So that if I reload this model, shall reload this model and shall works better. Yeah. The beauty of a live demo. Let us switch on. Yeah, lines match with the beam. So now if we use the inflate the proper location from the beam, no, that time it worked. And the reason why we have a crack here is because actually if we go to the orientation of those beams, we can see that yeah, there is a hard flip here from the elemental axis here. But that section has been done in an elemental axis which was totally different. So we have no real provision here to do the actual extension from one to the others. But for each and every element that has a consistent elemental system, we can do the proper interpolation of surfaces and shell mesh. So if we again do a Control Z and do a Control A and we'll get directly the shell mesh. So that I can go quickly through this one now to show the example I was mentioning before. So if I take my elements, so I do Control A and suppress each and every element. So I have here a solid. If I go not in Stiffener mesh, but in member mesh, just to seed some elements here. And I can even take an orphan line. I just need that tool, yet it's not generating the 1D. So you just need to select where and how many 1D elements you want to represent something. So here, I will generate an element size of 100. And I don't want an auto orientation, but use my own orientation here. And take my orientation vector along that direction. Sure, yeah. Mesh it. So I have 1D without any property which are assigned here. And going through this elastic section, we can see the original 1D element which exists here. And I will go from solid, pick that solid, and we can do a section for each and every beam. So, proceed. Now I shall go to the beam section. It's slower now, yeah. Now it has created a collection of elastic section, and we can see if I turn off the solid itself, you can see sections with a proper representation and fine details. And those beam sections are generated without any sketch. So the next extension of that tool will be to propose an option to automatically generate sketch out of the intersection. Then user will have provision to parameterize that sketch. And again, the moment you get that sketch assigned to it, you will get an engine and a 3D visualization from it. So that's pretty much what I have for today. Thank you.